Well, boy, we just love our acid.
It's time to wake up, universe.
Okay, guys. Hello, I'm Jerbear.
And I'm Sebastian.
And we welcome you
to Wake Up, Universe.
So, of course, we're a little later in the day. So, first of all, today we will be talking about acids and bases.
Yes.
Now, it's very important to know with acids to have some safety goggles, and as well as with bases and acids, if they are strong enough, you want to have yourselves some lovely gloves. We have some lovely gloves that are good for working with cleaning products, just as we will have. So today, in front of us, we have a few standard household acids and bases. Now, another standard household acid is orange juice. So that is what we are having a cup of right now, is some delicious orange juice.
And it tastes even better with our custom-made Wake Up Universe
mugs.
The cup.
And so, yeah. So anyways, let's just dive straight into it today. So, first of all, we have some pH paper. This is also called litmus paper. And so litmus paper, what it will allow us to do is look at the pHs of these different substances I have out in front of us. And I have this little pH color chart, which will do just specifically for our purposes.
And you see, when we dip this paper lightly into the liquid, we will see it will change color. It'll turn either more dark, more blue, or it'll turn more yellow, more red. The redder it is, the more acidic, and the bluer it is, the more basic.
Which is exemplified by the chart, as Sebastian has explained. So, anyways, let's just start with our standard substance. Everyone loves water. Now, first of all, let's draw pH on the board.
Now, what is pH, Jerry?
Well, first of all, let's just talk about what acids are. Acids, as we know them to be, are, well, see, first of all, let's take one of the acids we have here. Or no, let's talk about acids in general. So, first of all, there are things called ions. Ions are charged atoms.
Everything in the world is made out of little atoms, and those atoms have charges, positive or negative or neutral, but always positive or negative. Neutral doesn't exist.
The hydrogen ion has a charge of
plus. Exactly.
+1. The hydrogen ion has a charge of +1. Now, nature doesn't like this.
Nope.
So, what are we going to need?
We're going to need two of them. It's diatomic, which means we're going to need H2. That's where we find
Well, so naturally, in nature, hydrogen is H2. But when it's an ion, you normally find it as H+. Now, H+, it doesn't like to sit by itself. If we have a plus, what do we need to neutralize it? We need
a minus.
A minus. So let's take Cl, for example.
Chloride.
Those of you who know, Cl minus is chloride. We have HCl, hydrochloric acid. Now, it's only an acid when it is an aqueous solution, which means it's dissolved in water. So, though, let's look at our lovely pH scale. We have 7. We start down at 0 and we go up to 14. Down towards 14 we have the most basic, and down towards 0 we have the most acidic, 7 being neutral.
And 6
neutral.
and 8 are pretty.
Tend to see
neutral.
water down here. Tend to see bleach down here. NaOH as well. Sodium hydroxide. Down here we see that HCl. Way up here we see orange juice in here somewhere. Right there, or no, maybe right there we see vinegar, which is something we have here. Sodium bicarbonate, or baking soda, is right there. Maybe somewhere around in there, actually. But so this is our scale. These are our pHs. Now, pH looks like this. You have a lowercase key, a capital H. It means parts hydrogen.
And parts hydrogen is very important to understand because the number of hydrogen ions we have determines how basic or how acidic a solution is.
Yeah, and that's really important. So let's say we've got some water right here, and we put HCl in it, which it has to be because to make it acidic, it has to be aqueous solution. So what we have is water. Because it's a polar molecule, you see water has the O and the 2 H's. The H's tend to be more positive because the oxygen pulls more, making water something we call a polar molecule. So this side, kind of like a magnet, essentially, is what each water molecule is. Mm-hmm. So this side is more negative, this side is more positive. So what that allows is it pulls apart ionic bonds. It pulls apart the H plus and the Cl minus. The Cl minus goes towards the hydrogens, H plus goes towards the oxygens. And they don't bond, but they just kind of separate. It's a physical change, not a chemical change. So you have that in the water, and what you have is this separated H+. More separated H+, higher concentration of H+, more
acidic.
Parts hydrogen, more acidic.
And
yes.
you can think of water kind of like as like a robot with 2 arms. One arm will grab the negative part of, let's just say, like a neutral substance, and then the other part will grab the positive part. Opposites attract, although not, depends on, in real life, not really. But opposites attract generally in science, and so you will find the negative part of the atom of the molecule to take away the positive part, rip it apart.
So that is something to take note of. And so more parts hydrogen, more acidic. Less parts hydrogen, more basic. Now, parts hydrogen, you tend to see a very common very common ion, which isn't necessarily always true, but a very common ion down towards the basic side of things is hydroxide.
OH.
OH minus, right? Yes. So this is what we call hydroxide. NaOH example, KOH. There's lots of different hydroxides, and they are all what we call basic. Now, we also have carbonates. So carbonates or bicarbonates. So, for example, what we have here is baking soda. Baking soda is NaHCO3. Mm-hmm. HCO3 bicarbonate is minus and Na plus. You can also have Na2CO3 because CO3 is 2 minus. It has 2 extra electrons than it would need, 2 more electrons than protons, and Na2 is 2 Na pluses, makes it Na2 plus, right? Na2, 2 plus. So that is kind of, we'll discuss more on ionic bonding and why that is the case next week. We're going to talk about ionic bonding.
Oh, yes.
We'll have some hydrochloric acid.
Hydrochloric.
That is, we'll have some high purity stuff, so we'll be doing that next week. But this week we're just talking about acids and bases. So,
and stick around, we're going to have an experiment.
So, actually, we're going to start that right now. So, first of all, like I said, let's start pH. So, water is said to be the middle of the scale. Water is a covalent bond, and it's not, the bonds of it are not polar covalent, and we'll talk more about that next week with bonding. The bonds are not polar covalent bonds, although in general the molecule is polar. Actually they are, but we'll get into that. So first of all, let's just take our lovely pH paper and let's stick it in the water. Now this is not distilled water, so it might be slightly acidic, but let's look at our pH paper and compare. So if I'm looking at it,
I'll narrate what he sees. Ooh. Yeah?
yeah,
Yeah,
it's about 7.
That's actually pretty good.
Yeah, it's just as I suspected, because it's tap water. It is slightly acidic. I would call it actually halfway in between 6 and 7, if you look at the little chart here. So we call that about halfway in between.
So pretty neutral.
Right? So let's start to go orange juice, right? This isn't going to work so well because orange juice has color, but let's try it out.
And unlike the Swiss, this is not neutral.
The Swiss?
Did you get that? Yeah, Swiss.
So, actually, it is kind of working out for us. So if we look
Thank
here,
God.
it looks to be about a pH of 4, or 5. If I can say it's probably more towards. I'm gonna call it in between 4 and 5 again, as I'll show you here. So just as we said, orange juice is a little bit acidic because of the citric acid that is actually in the orange juice. Sebastian is adding a little bit more acid to his cup because he's getting thirsty. So, anyways, so that orange juice, because it has citric acid in it and water, oranges have citric acid because they are a citric fruit. That is why they say, citrus fruits, they have citric acid. So that's why orange juice is a little bit acidic.
And because of that, it's very good.
So, yeah, of course you don't want to drink, like, acids that are much stronger. There is another acid that we do have in foods.
Ooh.
Not necessarily one that I would drink.
Not necessarily.
This is vinegar, which is hydrogen acetate, also known acetic acid, HC2H3O2, and we'll get more into a little reaction we're going to do later. So it is going to be a little more acidic than our orange juice.
Way
so
more acidic, in fact.
if we look, it's, oh dear, okay, that's why I'm wearing these. So if you look down, it looks to be a pH of about 2.
That's very acidic.
Which is much less than the pH of about 4 that I would say the orange juice was. You can start to see the purple there, and there is your pH of about 2, or the acetic acid of vinegar. So that is that.
Good stuff.
Get another delicious taste of my favorite acid drink. And so let's start to look basic here. So I need to re-stir this again. See, as again, this is aqueous. So I have stirred up sodium bicarbonate, which is the same thing. Try and dissolve it. I did actually add too much, but some of it is dissolved in here. So this is probably, kind of like the orange juice, not going to be too far, but it is a basic solution. So if we look at that solution, hopefully trying not to touch it with my fingers here because I've already dipped into the others. But if we get that guy a little bit, you can see that it actually has turned, so this looks to be about a pH of 8. So like it's really not that far off from water. Water has a pH of 7, but you can see that this looks a bit like the pH of 8. So
it's barely basic. But we're gonna get down to the basics of basic.
So,
but I'm ching.
How about that? So, okay. The most basic substance in your house.
Ooh.
This is why we're wearing the gloves and the glasses.
Do not drink this.
Do not drink it. This is bleach.
I mean, it's highly... I mean, you can drink, but just don't do it.
Just don't do it. You see, it's going to cancel out your stomach acid. Because we'll get back to what happens when you mix acids and bases. So this is going to be a fairly basic pH. If we dip this guy into the bleach, I will show you that it has turned, oh wow. I would say this is, see, look at that, look at how blue that is.
Whoa, man.
I can smell the bleach as well. I would call this a pH in between 12 and 13. As you can see here, there is our bleach. And so there's 13. It's a little lighter, 12 and 13. So 12.5 is going to be our pH of the bleach. So that is our tests there. Now bleach, because of its very strong, how basic it is, it is not something you want to put a lot of things with. You may have heard, never put ammonia with it. It's because you were going to make chloroform. You can make some dangerous things by making some double replacement reactions. But a pretty famous and household double replacement reaction, which we will talk about in following weeks' reactions, is everyone's favorite, the production of carbon dioxide from vinegar and baking soda. So we'll add a little bit of baking soda here.
Prepare for a legit chemical reaction. And also, you can think of, now for those of you who are out here who are political geeks, or like politics, you can think of it in this way. The acids are like the Republicans, and the bases are like the Democrats. Now just think about this. The farther right you go, or the farther left you go, the more toxic it becomes. So like, if you have someone over here...
Leftist is actually Democratic, but well...
Okay, you're right, actually, that is true. I should know this by now. Okay, red would be Democrat, and blue would be Republican. Just gonna switch around the U.S. thing. So yeah, you do not want to get too extreme with the other, because an extreme base and an extreme acid will burn you.
See, that's the biggest issue. As we say with American politics, we need to achieve balance where everyone is happy. And that's kind of what nature wants to do, which is why when you put acids and bases together, you get water. And we'll get into why. You get in this case, we're going to get carbon dioxide.
Probably do that like in front of them, for the camera.
So, let's get some... I'm going to put this right in front of you here. You can see, and let's see.
See? And it's flowing.
Oh dear. Okay, so...
Oh, this is...
This is what happens when you have... And so a lot of that was C... Now, this reaction is not the best because it's not as pure, but I did try to get the purest of vinegar. This is distilled vinegar, so it is kind of the purest that I can get. But this, I can still smell the vinegar, but not quite as much. You can still see traces, traces of the sodium bicarbonate or baking soda at the bottom. There's still some vinegar, but mixed in with this vinegar and mixed in with the sodium bicarbonate is water. So let's draw this reaction on the board, shall we?
Oh yes.
Okay, so we have, we just did that reaction. What is it? So, like I said, we have sodium bicarbonate. Sodium bicarbonate. So bicarbonate is HCO3, as we mentioned, right? So this was 1 minus, this was plus. Together, they neutralize charges. You add vinegar, which was HC2H3O2, or acetic acid. So that, actually, what we have is a double replacement. So we see the anions. This is acetate. Acetate. And so the acetate and the bicarbonate actually switch. And so what we see is we see the creation of sodium acetate, which is also in the solution. Some of this white is actually sodium acetate. Quite a bit of it is, I'm sure. And some of it might be dissolved in the water already because I believe it is soluble. So some of it may be aqueous. No, don't drink that.
Okay.
Because there is still some vinegar in it, unless you want to taste vinegar. Go ahead.
Nah, I mean...
So, it's not the purest of reactions, because this isn't the purest of vinegar. It is distilled, so it's as good as I can get, So, but you can probably still smell a little bit of vinegar in there. And so these switched, the anions is what we call the negative ions. The negative ions are anions, and the positives are cations, we call them.
Actually, that's pretty good.
Did you actually
No,
think?
I'm actually like serious. It is. It tastes like what's that called again? Like like that European drink. No.
Champagne?
No. Not that I would know what that
Okay,
tastes like.
so anyways, NaC2H3, oops, I forgot the O2, so that's sodium acetate. And then this is going to have HCO3. So we have hydrogen bicarbonate. What happens with this is we see it split off into water and CO2. So the H2O,
Sorry.
and we see the CO2. So one of the O's goes here. So you'll see that instead you have one of the O's from the CO3. This becomes CO2, and O goes here, H2, H2O, CO2, and that's what we have released from this reaction. So the hydrogen bicarbonate, I don't think there's any traces. There might be some in here, but I'm fairly sure that most of it isn't. A lot of this is actually just water with the sodium acetate in it. So yeah, so that is that. That is the experiments of acids and bases.
I'm gonna regret that tomorrow morning. Yeah.
I mean, it is acetic acid, so it's not the best thing. So, anyways, you know what time it is today, or not? That's something we say at a different time. Today, it is time for today's Cash Craze.
Ba-dum.
Okay, so we're back. I just wanted to say we did have a question. So we had a question from Jody down there. Thank you for watching. So it is hydrochloric acid. It's not hydrochlorous. You see, because let's just get a little bit into the naming of acids. So let's say we have one of the what we call polyatomics. So let's see, nitrate, like our potassium nitrate, is a diatomic. It's NO3 minus. Carbonate is a diatomic, or not a diatomic, a polyatomic. What this means, polyatomics are essentially, they're ions that have multiple atoms in them. They're polyatomic, but they're typically, when you call them that, it is going to be, polyatomic ion. And they're, there's some negative ones. I'm trying to think of a positive polyatomic. None are coming to mind right now. Oh, yes. NH4 is a positive polyatomic. NH4 plus, that is. So let's just get into the naming of acids. So when you have, of course, an acid, as we said, parts hydrogen, always has an H or a couple H's. So because NO3 is, this is nitrate, by the way. So this is NO3 minus, it's nitrate. But we can also have NO2, I believe. NO2, I could go grab an ion sheet right now. But NO2 minus, let's look this up. NO2.
And these two right here, they're H-less. So they're not acidic. Not yet, at least.
Now, nitrite, which I will in just a second.
So yes, and more specifically, you're going to see right here, for those of you who don't know what all these letters mean, I'm going to make it a little more clear. This right here stands for, the N stands for nitrogen, O of course oxygen, and then right here you have the H for hydrogen. However, if you look specifically, you're going to see these little numbers. CO3 means carbon, one carbon atom, and then 3 oxygen. So just like, the numbers right here, they're actually, it's pretty simple to understand once you understand, basically. But yeah. And again, I just want to make this clear.
So,
these modes are amazing.
So, back to, sorry, nitrite is NO2 minus. This is nitrite. So, if, let's say HNO3 minus, so HNO3, because H is hydrogen, nitrogen, oxygen, 3 plus, right, plus and minus cancels. This is going to be nitric acid. This is nitric acid. But this here, NO2 minus, is nitrous. Right? If we have H, NO2, that is nitrous acid. So, this is the same thing. Hydrochloric acid. This is chloride. That's H, HCl. So we have chlorate. Hydrochlorous acid is not, actually, let me think about this. Because we have chlorate and chlorite. So chlorate is going to be ClO minus. And that is going to be, actually, I don't know the answer to that question.
Science is very complicated. I mean, it changes all the time.
So it does.
That's true. So again.
Yes, okay, so. Now, hydrochlorous acid is not a real thing. You have HClO is actually what we call hypochlorous. Hypochlorous. Sorry, I'm misspelling here. Is ClO or CHLOROU.
Write this down.
Acid. This is hypochlorous acid. So, HClO, as I have here, is hypochlorous acid. Hydrochloric acid is HCl, H plus and Cl minus. And so naming has a lot to do with polyatomics. So if I look at this, because this is carbonate, it is going to be carbonic. Just like the nitric, this is carbonic acid. But if I were to have carbonite, carbonite would be named, which is CO2, I believe, minus, carbonate is CO2 2 minus. That would be H2CO3 is carbonic acid. But HCO2 minus, I believe, is what carbonite is, would be I don't even know if carbonite is a thing. But so, you get the whole point. So that is kind of the deal with that. Nitrous versus nitric. Nitrous acid is HNO2 versus HNO3 nitric. So because this is nitrate, that would be nitric acid. Because this is nitrite, it would be nitrous acid.
And you can trust that.
So sort of comes with chlorine. Chlorine is kind of weird. Hypochlorous instead of hydrochlorous. It's kind of weird. But just as well, things like HCl or if it... See, we just call this nitric acid, you see. Nitric acid, I mean. You see, it's H plus a polyatomic. But if you just have H and just a single ion, like chlorine, Cl minus or F minus, that is going to be called hydrochloric. And you always call it ic. So like anything, first of all, we can talk more about nonmetals again next week. I can show you on the periodic table. But what it is that anything that is a nonmetal, kind of looks like that shape on the periodic table, anything that's a nonmetal tends to form negative ions. Anything that's a metal over here, hydrogen, sodium, tends to form cations, positive ions. And so what happens is you have your negative ones down here, and so that forms... we never got to cash craze. We'll get back to that in just a second. So because you have those nonmetals, they form, ides. That whatever you see, we would call this hydrochloride. Like sodium chloride is NaCl, right? Salt, sodium chloride. Just as well, we also have, anything down here ends in ide, right? O2 minus. So you have HCl, it's hydrochloride or hydrochloric. So any acids always that are ides end in X. So that is why this is hydrochloric acid. HF would be hydrofluoric acid. You know, that is kind of what we were getting at with all this stuff. That is the whole point of naming. It's a completely new thing to talk about to kind of cover all that. I hope that answers your question, Mr. Joe D. And yeah, so that is that. So let's dive straight into today's cash craze. Today we're going to talk about Google, and we're going to talk about Apple. So first we're going to open with, you tell me the time.
We're going to start off, what?
So we're going to start off talking about Apple. Apple stock prices right now. Apple stock price last time market was open, and so last time Apple stock prices were $190.24 on Friday. They went up $3.37 since the last share price. This is share prices for Apple, and it went up 1.8%. So let's just take a look at, like, Apple's graph has been kind of slow. You know, they've been dipping, they've been, you know, yeah. So I'm going to say probably within the next 2 weeks, if you look at their more yearly basis and you look at how they've been doing, they kind of spiked up a little bit. They had some busy stuff down here. It's getting a little busier up here, so maybe overall next month or so, you can expect that share prices are actually going to be a little bit higher for Apple. So try and buy it a little bit now. It's going to go up a little bit. I don't assume it's going to be a lot, but share prices are going to go up about in the month. And I would say, looking at where they're going to go soon, they're probably going to go down a little bit soon. So soon, it's going to take a little dip, I'm going to assume, and then you can buy some stocks, because this is kind of what it looks like now. It's a little slow, just ups and downs, kind of plateau-like. So it's probably going to take another dip because we haven't seen too much. This is when to buy. You wait till the end of the month. It's probably going to be a little higher, maybe, you know, a couple bucks more than the 192. So you can make a couple bucks. Apple, pretty stagnant right now. If we look at Google share prices are currently up to $1,135 per share. So that is the current share price for Google right now. Google, I mean, it kind of has the same look. It's kind of unfortunate. Google has this jump like that, comes back down, kind of slowly wakes it back down, and it kind of goes up and takes a little dip, up again, and so we see a little activity down here. I assume that Google stock prices are actually going to go up, so it's time to buy them right now. I would assume maybe in the next couple weeks, those share prices are going to be a little higher, but then we're probably going to see a little more stagnance, because it does appear to start to be going, or no, actually, I'm sorry. This is what has already happened, so forget buying them now. We started to see some jumping, and it went up. So this is where they are right now. They're higher than they have been throughout the past month right now, so we're a little stagnant. If you look at their annuals, it looks like May has a little bit there. So like I said, maybe next month, next 2-3 weeks, you should be able to see some higher share prices. See, because right now they are up $35, so it was $1,100 per share last market. So this is with last market close, which was 8 o'clock yesterday, on Friday. So that was 8 o'clock yesterday. And so they are up 3.18% from what they were. So share prices probably, you know, next 3 weeks, end of the month, that is when share prices are probably going to go up a little bit. But again, we're seeing some economic stagnance. So also, you know, kind of some impacts. You know, countries like China, Canada, Mexico are actually starting to impose tariffs on American goods, so we're starting to see some
trade war,
reciprocal tariffs, and we are seeing the trade war come through. So anyways,
to find out what happens,
you know what time it is.
it's time for the wheel
of mythic technicality.
Technicality, let's go.
Alright, so let's just do our spinning.
For those of you who don't know, this is what we do every time. Oh. It's going to be a
commentality.
Bum, bum.
So I am going to put the link in the description once this video has gone online, I am going to add into the description a little friend of ours. This is a loyal subscriber of mine. So I need you to go send some love to his channel. This is Marshmallow is the young man's name. So
It's
Marshmallow. It's not actually his name, of course. Marshmallow is here. I'll find him. He is a subscription. I subscribe to him just because, you know, I think he's got a quality channel of, you know, that will be going. He needs some people to go watch his stuff. He's let's see, it's Marshmallow 3000. So as he says in his latest video, he needs his help. You know, I want to link you to his Universe Box video, where I think it's kind of cool. I see a young scientist following the path. He makes this box and he calls it his Universe Box. And I think he has some interesting approaches to things. And so if he would like to contact me as well, he can, because the Jer Bear email is in the description. I really appreciated one of his comments. He said, wow, I have to say this is cool. And I believe it was the dimensional doors. So I'm telling you all to go leave some commentality. So in the description, I want you, not in the description, in the comments to the link of the video, which I will leave, the Universe Box, I want you to give some love to his channel and write hashtag, hashtag commentality and WUU.
WUU.
So hashtag commentality WUU for Wake Up Universe. That's us. If you want to feature yourself saying this is my name, so like I said, whenever it lands on Win Face, we are going to give away one of these beautiful mugs.
Beautiful, custom
and it
made.
is going to be the Wake Up Universe mug that we can get from the Jer Bear merch store, which is in the description as well right now. You can get yourself the mug. But what's going to happen is I want you guys to send videos to the Jer Bear email, which is in the description down there, jerbear333@gmail.com. Send a video of yourself saying, hello, this is my name, this is where I'm from, so I'm from Plymouth, Michigan, and hi, I'm Jer Bear, or Jerry Brewer, from Plymouth, Michigan, and this is my win face. And you'll give us a pose, and you're going to say, and now it's time to spin the wheel of technicality. And so what's going to happen is, when it lands on a win face, we are going to pick one of the people who has done that. So in the beginning, we are just going to be giving them away. If we get a whole bunch, then we're going to be doing a raffle. But as of right now, no one has sent us any videos. So what we're going to have you do is you're going to send us a video, and we're going to have like the first person and the second person. And you know, whenever it lands on it, we're going to say, oh, the first person was this person who sent it. And then it lands on it again, we'll give it to the second person, etc. And so that is how you can win yourself some free Jer Bear Wake Up Universe mugs, specifically Jer Bear and Special. We have the Wake Up Universe mugs that you can also buy from the store right now if you would like, along with some other Jer Bear stuff. These lab coats I bought individually. These are not actually on the store right now. Tell me if there's any interest. Again, email or comments. If there's any interest in these lab coats, I can get your custom name on there. They are about $32 a piece. So,
if you have the money.
But, you know, I don't actually know how we could do that, but I could, you know, send you my address. You can send in the check in the mail, and I would gladly order it out to you, and I'll be sending you the Amazon receipt. So I'll give it as a gift. Just as well, tell me if you would like. I was thinking of getting some Wake Up Universe patches to put right here on them. Unfortunately, they are about $10 a piece. So I can only order a minimum of 10, and they have to be $10 a piece. So if it's interesting, just let me know. If you would like a Wake Up Universe logo patch for $10, just let me know, because I've thought about ordering those as well. It would be the same thing. So if that is interesting to you, please let me know in the either comments or send an email for private contact. And also, you can send a direct message via the Jer Bear Instagram account or the Jer Bear Twitter account.
We have a Twitter?
So we do.
A Twitter?
We have the Jer Bear Twitter, Jer Bear and Wake Up Universe. So I hope you did enjoy this episode of Wake Up Universe.
As always, I'm Sebastian.
And I'm Jer Bear, and we will see you all later. Next time. And so next time, though, just as well, we will have a lovely background, which I have ordering, and we're going to be messing around with ionic compounds in some high-purity hydrochloric acid. Do not try that at home.
Very dangerous.
And so, as always, thanks.